All right, so what we're going to do inside of this video is we're going to take a look at the inference review and talk about what kind of test I'm going to use at what time, right? So I'm reading a scenario, and what I want to do is I want to think to myself, what kind of test am I going to use and at what time, okay? So we'll start out, right? So we've got a machine, it's at a soft drink bottling factory, and it's calibrated to dispense 12 ounces of cola into cans. A simple random sample of 35 cans is pulled from the line after being filled, and the contents are measured. The mean content of the 35 cans is 11.92 ounces with a standard deviation of 0.085 ounces. Okay, and then this says estimate the true mean. Wow, okay, so this is not actually going to run a test, right? Okay, we're looking for an estimate, and so what I'm going to do is I'm going to estimate my mean, and I've got a choice between two different kinds of intervals. The first interval that I'm going to be looking at is either a t interval or a z interval. So think to yourself, okay, well, which one am I going to use and why? Okay, the t interval would be, the z interval would be if I actually have the population standard deviation. I don't. So no population standard deviation. So I'm going to use the t interval. Okay, how do I know? I'm looking for the mean contents. Cool. There it is. All right. Number two, for a class project, a political science student at a large university wants to estimate the percent of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Okay. Compute a 90% confidence interval for the true percent of students who are registered voters. Since this is a percent, I know that another way to think about a percent is as a proportion. So I'm going to be running a proportion test, okay? And if you notice, I only have the 500 students, okay? So I only have the 500 students, and so consequently, what that is that tells me it's going to be one sample. So it's a one sample proportion test. Or not a proportion test, excuse me. Confidence interval, one proportion interval. All right, cool. All right, so, and really we've got, a couple of different intervals. We'll talk about those in just a second, okay? Now, let's say, for example, we look at number 3. So insurance companies track life expectancy information to assist in determining the cost of life insurance policies. The insurance company knows that last year, the life expectancy of its policyholders was 77 years. They want to know if their clients this year have longer life expectancy, okay, on average. So the company randomly samples some of the recently paid policies to see if the mean life expectancy of the policyholders has increased. Okay, so they want to know, does the mean life expectancy, has it increased? Okay, all right. What you want to notice here is that we're actually comparing against an old number, an old value. Okay, the insurance company will only change their premium structure if there's evidence that people who buy their policies are living longer than before. Okay, and they had a mean before of 77 years. We've got that information right there. The first thing that it tells me is that I'm going to be doing some kind of means test. All right? And since I'm making a comparison of the mean to a value or number, right, a previously declared value, that actually is going to tell me that I'm going to be doing it with one population. That population compared against the value. All right? One population implies to me that I'm going to be working with one sample. Okay, one population, one sample. So we have a one sample means test. Now, since it's a one sample means test, I do need to figure out whether or not I'm going to be running a t-test or a z-test. And again, just like before, we have to ask, do I have sigma? Okay, so there's that question. Do I have sigma? And the answer is no. If you go through and read through here, we do not have sigma, right? So it's a one sample means t-test. And there we go. Okay. One other way to think about this is to think about it as with the null and the alternative. So my null hypothesis, if I go through and read here, is going to be my H naught is going to be mu equals 77, right? Okay. The life expectancy, which is a quantitative variable, is 77. So that's my null. And then my alternative is that mu will end up being greater than 77. All right. Notice one mean. So that's a one means test. And why is it a t? Because I lack sigma. Okay? All right. Now, a large city's DMV claimed that 80% of the candidates passed driving tests, but a survey of 90 randomly selected local teens who had taken the test found only 61 had passed. Perform a test to see if the pass rate for teens in this location is significantly lower than the DMV claim. Okay. Now, what I want to do now is I now want to think about what's the variable that's actually being tested. Okay, what's the variable that's being tested? And if we notice, the claim is that 80% of the candidates pass the driving test. That's a percentage. What we want to remember is that a percentage and a proportion, if we're looking at the percentage of people who have a particular thing, not like a test score. A test score as a percentage is actually a quantitative variable. But in this case, it's what percentage of people actually have the characteristic or quality, right? That means a categorical variable, and so that percentage is in fact a proportion, okay? We also notice, if I write my H naught is going to be that P equals 0.8, and my HA, okay, we want to perform a test to see if the pass rate for teens in this location is significantly lower than DMV claim, so that's going to be P is less than 0.8. Notice again, we've got one population. Just the group of teens that we're testing here, okay? And also that we've only picked out 61, or we've got 90 kids here, so we've also got one sample. What does that mean? That means that we're going to be running a one sample proportions test. Okay? All right, 48% of 500 students randomly sampled from College A drive to school. 67% of 625 students sampled from College B to drive to school. Estimate how much more of a proportion of students from College B drive to school compared to the proportion of students from College A. Okay, so when I look at this one here, all right, I'm going to notice a couple things. One, first, that these are percentages, okay? And they're percentages of a certain amount of students. And so consequently, that tells me that I'm going to be running a proportions test of some kind. But I also want to notice that I've got a group of 500 students here, and I've got a group of 625 students here, and so hence what I've got is I've got two samples. I've got two samples, right? So this tells me that I'm going to be running a two-sample proportions test. That's the key difference. We're comparing proportions in this case, and we're comparing proportions from two different populations. That's what makes it a two-sample test, right? Two different populations. And so let me write those. Two populations. And those populations are College A and College B. Okay. Number 6. Two researchers investigated the reliability of test assessment. One group consisted of 30 students who took proctored tests. A second group consisted of 32 students who took tests online without a proctor. And the two samples were taken independently and not paired or matched. Ha! Well, there you go. Not paired or matched. The two samples are independent. Okay. Oh, and there's two of them. There we go. Now, I may not be quite that blunt, but that's pretty darn blunt right there, okay? What we want to notice is one, what are we comparing? We're comparing our X bars here, okay? So there are two of them, two means. Two means are compared. They are from independent samples. One of the other ways that we can tell that they're also from independent samples is, and this is not always true, but it's true in this case, that our sample size for both is different. So we have n equals 30 as the sample size for one of them, and n equals 32 as the sample size for the other one, right? Since they have different sample sizes, they can't possibly be paired. Remember, pairing is where we match them up. We can't do that if one has 32 in it and the other one has 30 in it. So consequently, what that tells us is that they're not actually paired. Right? See, these are not paired. Paired? And so, since we have a not paired test for means, we have what's called a two-sample means t-test. Ta-da! What do you think? Two means, right? Okay. Independence means, in this case, independence means that we're pulling them from two different groupings, okay? Right? And in this case, the groupings actually are not the same size. So that's why we have a two-sample means t-test, okay? Right? We don't want to make this too difficult. How many samples, right? What kind of variable are we testing? In this case, means, yes? Okay, then that should actually help us with what we're doing, okay? All right, good. Number 7. Two researchers investigated the reliability of test assessment. One group consisted of 30 students who took proctored tests. A second group consisted of 32 students who took tests online without a proctor. The two samples were taken independently and not paired or matched. Assume the conditions for the inference procedure are met. Use a 0.01 significance level. All those things are great, right? Notice how many groupings we have. We have two samples, or two groupings. Okay, and what we're looking at or what we're comparing are means here. So this is a two-sample means test. In addition, just like the last one, what we had is we had two groupings that were actually different sizes. And since they were different sizes, that tells us they can't possibly be matched or paired. It also says they're not matched or paired, right? So that means that the samples are independent. Cool. Yes? Number 8, 42 men and 54 women were randomly selected and asked if they prefer vanilla or chocolate. 27 men said they preferred vanilla, and 28 women said they preferred vanilla. Is there a difference in preference between the two genders? Okay, this one is a little bit trickier, all right, but not too much. It's a categorical variable, okay? Notice a categorical variable here. In particular, liking vanilla. That's our variable. Liking vanilla, right? And we have two samples. We've got one of men and one of women. They have to be independent, or at least they are independent in this case because they're different sizes. We can't possibly pair them, right? And even so, even if it were the case, it doesn't really matter because this one is a proportions test. The reason why we know it's proportions is because it's the categorical variable. For the purposes of what we're doing in the class for this semester, okay, if we're comparing two or fewer proportions, we're comparing, or two or fewer categorical variables, we're comparing proportions. Okay? Categorical variable, proportions. So this one here is a two-sample proportion test. Ta-da! All right. You do not need to do 9. 9 is beyond the scope of the class for right now. Okay? Or 10. Nope. 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 Well, this at least is some good work here for number 13. We look at this totally different kind of work that we would be doing. So that number 13 says the income of a courthouse and the salary of justice at the courthouse are recorded. Notice that the income, right, this is a quantitative variable, and the salary of a justice is also a quantitative variable. So what we're looking for is we're looking for a relationship between two quantitative variables. And since we're looking for a different relationship between two quantitative variables, we're going to be doing correlation and regression. Okay? Two different variables, right? Just like we've been doing thus far today. On the one hand, right, we have over here, here's our justice salary, right? That's going to be our Y value. And here's our court income, and that's our X value, okay? The only kind of test that we do where we're going to make a comparison between those two kinds of quantitative variables, two different quantitative variables, is regression and correlation, okay? That's it. And primarily, this is just so that you kind of understand that that's what we're looking for. a relationship between quantitative variables. Okay? That's it. So that's how I know. I mean, there's other things too, like it's got a scatter plot. And yeah, lots of other stuff. We have a regression equation. Here we are. Okay. And that concludes the video.